we're talking about friction, I want everybody to remember that it's not an active force. Friction is a reactive force. You could even just say it's a resistance force. And what you really could say is that its strength, sorry for any lag in the video, its strength depends on the surface qualities, at least in part, of the two materials that are rubbing against each other.
Obviously, because you're going to find less friction when you ice skate than when you're just walking.
That's right, yeah. So you might talk about, when you talk about surface qualities, one of the things that you might consider really is like how bumpy those two surfaces are. You might want to talk about surface 1 and surface 2, and if surface 1 and surface 2 are extremely bumpy, it makes sense that those bumps are going to interlock at some point. You actually might think of them kind of like teeth fitting together. And if these two surfaces nestled in next to each other and they actually sat against one another, you can imagine the teeth really actually interlocking with each other, something like this. I mean, this, unless I told you that this was two surfaces touching each other, you'd think that it was just a squiggly line with two angled lines at the ends. But what I'm saying is that these two surfaces could lock together. And if they lock together, and those teeth are sort of stuck together, you have a little bit of traction. And you can imagine that it's a little bit hard to unlock the teeth. The traction is a little bit hard to overcome. Now the thing is, once that traction gets overcome, in other words, once I get these two surfaces sliding against each other, do the teeth interlock with each other, or do they just sort of skip across one another? They skip across. And so that actually brings me to a kind of an important point. Not only does the strength of the friction depend on the quality of the surfaces, the roughness, if we want to talk about traction, but it also is affected by whether the two surfaces are stationary relative to one another, or if they actually are sliding across one another. Turns out that when they're interlocking...
Differences between static and kinetic friction.
You're getting ahead of me, and I'm going to ask you to wait for me to talk it out, because I know that you've talked through it before. Right? We want to talk about this surface here being stuck together a little bit more because the teeth are interlocked with one another. Okay? And so people call this a static situation. And when these surfaces are sliding across each other, we call it a kinetic situation. And since we're talking about friction, exactly as Sam said, we have static friction and kinetic friction. And when we talk about kinetic friction and static friction in terms of variables, we're going to use Fs for static friction and Fk for kinetic friction. Now, having said that, for the same two surfaces rubbing against each other, you tell me, like based on what was just said, you tell me, which one do you think is stronger, Fs or Fk? Yeah, Fs. You know what? I can't think of a situation where it's not true. And physically, traction-wise, this mechanically makes sense to me. Okay? Now you're going to get some people that are maybe more chemistry-oriented, and they'll say, hey, friction isn't just about traction. It's not just about uneven surface interactions. That's not the whole story. Those people will say, hey, even if you had two perfectly smooth, imagine there were two perfectly smooth surfaces against each other, they actually do have friction. You can't have two perfectly smooth surfaces rubbing against each other and expect there to be no friction. So traction can't be the whole story. And they'll say, what you're forgetting to tell these kids is that there are atoms in this particle or in this material and atoms in this material, and each of those atoms have electrons orbiting around them. And sometimes electrons wander across surfaces, and talk about some sort of ionic cohesion. Well, that's really not my business. Not at this level, okay? And I don't want to say that we're going to just ignore its existence, so that we've acknowledged it a little bit. We're just going to talk about this stuff. Everybody cool with that?
Yeah.
Okay, so I'm not going to ignore this. I'm not going to say that this isn't something that somebody at some level of complexity or detail might care about someday. That's not what we care about right now. Okay? The other thing that we're not going to acknowledge formally, but I'll acknowledge it quickly, is that if I have two surfaces that are rubbing against each other and one happens to have the quality, like for example ice, oops, it'll come back. If one happens to have the quality, like for example ice, where when I rub the top surface against the bottom surface maybe experiences friction such that it melts a little bit, it picks up some of the kinetic energy, and that kinetic energy gets turned into thermal energy upon friction, and then you get a thin melty little layer here, and that thin little melty layer, you might call it like a laminate fluid layer, or I don't know, people make
slush.
You could call it slush. But when you're ice skating, it's not really slush on the surface of the ice. It's a really, really thin, melty layer. That's a complicated idea because it eliminates this bumpiness. And it doesn't really talk about this ionic interaction thing. It's just saying that there's like a watery lubricant on the top of the ice, and that makes the friction go down a little bit. So we're gonna disregard this idea, and we're gonna disregard this idea. But in the backs of our minds, as humans that have lived in the world and all that sort of stuff, I want to acknowledge that they exist. Okay, so I don't want to be like oversimplifying the story. We're just not going to deal with it in our analysis, right? So we've got static friction, and maybe we'll put it in writing. Static friction is the resistance force experienced by an object, or we could say exerted on an object, but I'll say experienced by an object, that keeps it from moving. It's the force that has to be overcome, in other words, in order for you to get it moving. So if the static friction force was 10 newtons between two surfaces, it wouldn't go anywhere unless I pushed with greater than
10 newtons.
10 newtons. That's the threshold, okay? So you can think of static friction as kind of like a threshold to get it going. We also have kinetic friction. I like to say that that's the resistance force experienced by an object already in motion. Or I say an object while it is in motion. So people might give you a method to calculate the static friction force, and you might find a method to calculate the kinetic friction force for two surfaces that are rubbing against each other. And if you're able to push with 20 newtons, you have to check, does that exceed the static friction force? And if it doesn't, then the thing don't go anywhere, and the velocity is zero, the acceleration is zero. But if it exceeds that friction force, that static friction force, and it is moving, then you disregard the static friction force and you deal with just the kinetic friction force. You don't deal with both at the same time. It can't be moving and not moving at the same time. That's just illogical, right? At least in the world that we live in, Heisenberg uncertainty principle and all that notwithstanding.
Schrodinger's cat.
Yeah, multiple states of reality.
Now Schrodinger's cat would be like an awesome Halloween costume. You draw like a line, you have like a cat costume, draw a line on your face, draw a line down it, and on one side, draw like an X over your eye.
Yeah. We could have a cat. All right, moving on. All right. So we've got these two definitions for friction, these two ideas of friction, and you've experienced it. You probably, even if you, if you have a chair, this is a horrible chair. That's a chair, believe it or not. Modern Art Deco chair. And if you take this chair and somebody pushes on it, until you're F applied, if you're able to push perfectly horizontally, exceeds the Fs, that chair isn't going anywhere. Once the F applied does exceed the Fs, now we would disregard Fs
And you would get the chair moving.
Well, no, then you would talk about what the F net is, and the F net in this case would be the applied force plus, not the Fs, but what would you say? It doesn't always have to be the same person answering. Yeah. Fk, yeah. And so I might go about drawing a free body diagram that could look something like this. I could say in this case, I might have an F applied and an Fk. And you notice that I haven't drawn it to a perfect scale or anything because I have no numbers. But if you look carefully, I tried to make my F applied a little longer than my Fk, implying that this thing would be moving. And of course, we'd have our F normal and our Fg. Okay, this could be a nice simple free body diagram related to this sort of thing. I want to take a look at another free body diagram, maybe something a little bit more complicated. But let's just say that we have an object slightly more complicated, not much. An object sitting on a surface, and no, that's not a hat. This isn't like the Little Prince or anything like that. It's an object sitting on a surface. And if we have Fg equal to 200 newtons, let's just say that we were given the mass of this thing and we'd already calculated Fg. And this thing is sitting on a surface, just sitting still at this point. F normal would be equal to 200 newtons as well. Now if we apply a force of 15.0 newtons, there could be some force due to friction. I'm just going to label it as FF, not as FS or FK at this point, because I don't know whether it's one or the other. So people often use FF as sort of like that ambiguous. I'm not quite sure whether I want to commit to FS or FK right now. So it's force due to friction. Sometimes they'll write it as force fric, just because somehow it makes them feel like, you know, frickin' frack, I need to figure this thing out. So from there I want to say how people have defined the kinetic friction force and the static friction force. What we said before was that the strength of the friction force has something to do with the surfaces between these two, but what it also has to do, what I didn't really acknowledge, was how hard those two surfaces are being pressed together. And you can do an experiment like really easily with this. You take your hands and you rub them across one another while you're pushing lightly. It's easy. When you push them hard together, you haven't changed the surfaces, it's harder, right? So the pressure between two surfaces affects the degree of the friction. That makes total sense. It's within my human experience, and I can't think of a reason to debunk it. So what people have said is, we could talk about some sort of a description of this ratio of how hard you press against or press two surfaces together related to how much friction is experienced. Turns out that this ratio of force due to friction divided by the normal force, that's the pressure force between the two surfaces, gives us what we call the coefficient of friction. And that coefficient of friction describes how frictional the two surfaces are when they rub against each other. Once I do this for one normal force, that's like for one pressure force, pushing these two surfaces together, turns out that that coefficient of friction is going to hold up for any different normal force for that exact same pair of surfaces. Okay? So for a particular pair of surfaces, let's say wood and glass. Let's say that we did this. We actually figured out. Yes, ma'am.
Is that supposed to be an M or a mu?
It's a mu. Oh, thank you very much. So many of you haven't seen the letter mu before. The letter mu isn't an M and it isn't a U.
It's a mu.
It's a mu.
Knew you were going to do that.
Well, it's true. So we have this mu here, M and M, sort of like an MU mix, but it's actually it's a Greek letter. So it's not like we're inventing it or anything like that. Like it's an actual letter. So the Greek letter mu is what you use for the coefficient of friction. It's not an M. Okay, it's not another mass variable. So don't get that confused. It's got sort of a hump in the middle, a sagging hump in the middle, and that's on purpose. We could experimentally figure out this mu value. What you could totally do this. If I rearrange this equation, I could say force due to friction is equal to mu times F normal. And if I were to take this equation here, I could actually build some data for this from a graph. In fact, the graph that I would make experimentally would look like this. I would have an x-axis of normal forces. And I could have a friction force, y-axis. What I would do, I'll tell you how I would set up this experiment, and I can show you in the lab in a little bit, is I would take a block of wood, I'd put it on a board, and if I connected this block of wood to a force sensor, I'll just put a little dial on it here, and I pull on that force sensor. Every time I pull on that force sensor, I would get a reading. Okay? And that reading, if I can just pull on it so that it moves at a uniform velocity, that reading would be the force due to friction. Because that would be the force that's resisting how much I pull on the thing, if I can pull it at a constant velocity. Because if this free body diagram was a balanced free body diagram, in other words, if I wanted this block to slide at a constant velocity, what would the friction value have to be if my applied force was 1500 or 15 newtons? Yeah. Yeah, it would have to be 15 newtons if I was to get it to move at a uniform velocity, right? This would be the kinetic friction in that case, but that would mean that I'm moving at a uniform velocity. I would have a friction reading that would show up on this scale. Now, if I stacked more and more stuff on this, what would that do to the normal force at this surface? It would increase it, right? And as you would expect, what would that do to the friction reading? It would increase it. In fact, what you would get, and we can do this afterwards, we can actually get the spring scales out and we can measure in newtons this exact scenario. What you get is a set of data that might look something like this. Yes, sir? No, if there's 15 newtons this way and 15 newtons this way, and it's moving, then it's just moving at a constant velocity. Yeah, you're right, but it's got a uniform velocity. If I hadn't gotten moving in the first place, that uniform velocity would be 0. If it was sliding, uniform velocity would carry on as it is. And so you might develop a graph something like this one here, where as I increase the normal force, that would increase the friction force. It's a direct proportionality. Now, if I look at this graph, maybe I'll add a line in there. Put a line of best fit. As I look at this graph, it reminds me an awful lot of those grade 9 days. You remember when you had your y equals mx
plus. I was just going to say that it's a linear relationship.
That's right, it is. Now, where's the intercept? I hear people whispering. What is it? It's 0, right? All right. So the y-intercept is 0. So we've got y equals mx plus b. Now in this case, we didn't use y's and x's. We used ff and fn. The y is the fn value or ff value, and the x is the fn value. And now we get to this point where we say, okay, so ff is equal to mfn. Hokey doodle. That's where they got the equation from. Can you see that? It's just that instead of using m for slope, like we did back in grade 9, we're going to use mu to specify that we're talking about a coefficient of friction. Okay? So this is a quick little thought experiment, and we can pull out the real lab equipment, no problem. But if you can follow the thought process, that's where that equation comes from. It's not some magic equation that comes from nowhere. It's totally based on logic. All right. So having said that, I want to differentiate between Fs and Fk. It turns out that we could do this exact same experiment for an object sliding while you pull on a spring scale, and do the exact same experiment for an object that's stationary. Just pull it until it just budges, and you can get the static friction force in that way. So you actually end up with two remarkably similar equations. Fs is equal to mu times F normal, and Fk is equal to mu times F normal. Now the thing is that Fs and Fk represent static friction and kinetic friction, but these two right-hand sides look identical to each other. So the way we differentiate is that we call this mu s and mu k. In other words, we have a coefficient of static friction
and a coefficient of kinetic friction.
You hit the nail on the head. Oh, sorry, I'm off the page. And a coefficient of kinetic friction. I always like those the rap videos and things like that. They always have like a hype man or something. You could totally be my hype person. I love it, Sam. What? coefficient of static friction. Friction in the house. All right. So we've got our two methods for calculating friction, whether the thing is stationary or whether it's in motion. Now, if you're talking about wood rubbing against glass or whatever, you might be dragging any two surfaces against each other. But let's just say hypothetically, let's say that I did this experiment and I found one of the coefficients of friction for wood rubbing against glass to be 0.0050, fine, whatever. I just made up that value just so you know. So don't go look it up and tell me that's not really it, okay? And I found the other one to be 0.0120. You tell me, based on our conversation so far, which one of those guys is the static friction coefficient? Which one of those is the
bigger one, because the static friction is always going to be greater than the kinetic friction. Is that what you said?
Yeah, that's exactly what I said. We got to say it more hype man style, though.
Yeah, sorry, it's just I couldn't really remember.
Okay.
Because I thought it was the other way around. I'm sorry, I'm tired this morning.
Yeah. So mu s is greater than, oopsie daisy, mu k. Okay, and that would be our logic there. Now, you're almost universally going to figure out which one is which beforehand. But if for whatever reason if for whatever reason you ever got confused.
Sorry, duh. I thought the 5 was over there. My bad.
Okay. Yeah, you thought maybe there's decimal place.
Yeah.
If you ever get confused, though, for whatever reason, and you have two values and one's bigger than the other, it's a good rule of thumb that mu s is greater than mu k. So don't let it confuse you, because the mu's are plentiful out there sometimes. That's my muse. Let's try a problem. I've got a...
Mr. Killens, do you mind if I go get a drink?
No, go for it. So we've got an example problem. I'm not sure how many example problems we're going to do, so let's just try with this one first. Let's say that I have an object sitting on a surface, and let's say that we have an FG value of 200.0 newtons. Somebody give me a shout out. What would the normal force value be? Yeah, assuming that nothing's pushing down on it in any funny way to increase the normal force. We've talked about that. It would be 200.0 newtons as well. Now let's go back to our scenario we drew above. We said that we might want to apply a force. I'm obviously not doing this to scale. Let's say that we applied a force of 15.0 newtons to the right. 15 is definitely smaller than 200, so don't give me a hard time. Obviously this is to scale. Is not to scale. And we'll say that this object experiences friction, and I don't want to commit just yet as to whether it's kinetic friction or static friction, so I'm not going to write K or S. I'm just going to write F fric or FF. Okay. What I will say though is that I've investigated the situation. I did the old drag the thing across the table routine. I figured out what the mu coefficient was for static friction and kinetic friction, and what I found in my experiments is that 0.0500 was the static coefficient of friction, and mu k was equal to 0.0400. And so I want to figure out what these two friction values would be. Tell me what I should do. I'll state it as a question. What is Fs? What is Fk? You know what? I'm going to carry through with writing out my answer, and I'm going to ask you, because it's a fairly straightforward calculation, I'm going to ask you to do the calculation, on your paper, okay? And we'll meet up and we'll trade stories here as to what our answers are. Don't forget to always write your equation before you sub in. heard somebody asking, sort of whispering to a buddy there, what are the units on the coefficient of friction?
There are no units.
Well, I'm getting there. I want to point out that mu s, as we said before, was equal to Fs over F normal. And keep in mind that the units for Fs are newtons and the units for Fn are newtons. So Sam's right. The units cancel out and the coefficient of friction is a unitless, and the coefficient of friction is a unitless value. Okay?
It's just a magnitude.
Just a magnitude. So it's just a description of how those two forces interact with each other. So just so you know, don't panic that it doesn't have a unit. I didn't forget the units. I just forgot to explain why it doesn't have any. Alright, so 0.050 times 200, I get 10.0 newtons, and I get 8.0, actually I guess I get 8.00 newtons. Yep.
So this type of questions is going to be a certain like positive or negative?
Yeah, that's where it's just going to go next.
Oh, okay.
Yep. So whenever we draw a diagram like this, we might want to talk about having our up and our down, our right and our left. I would say left is negative, up positive, right positive, down negative. That's all reasonable to me. And so at this point here, although there's no allowance for positives or negatives in the equation, this equation really relates to this picture. I can see that Fs would be in the negative direction and Fk would be in the negative direction. There's no place for me to put a negative sign when I sub in the variables. It's just not there. But by interacting with my diagram, I know where the negative sign, whether it should be a positive or negative sign, and I say that to the left is negative here, so that makes sense to me. Now, when I go back and look at this, a reasonable part C for this would be find the net force. How would I find the net force? I mean, we've talked before about how you use free body diagrams to write your equations for F net. How would I write the net force equation for this one? Somebody help me out. Somebody who's feeling brave. Maybe somebody that wants to impress somebody. Oh, hi. Yeah, I think so. I mean, we could specify that it's F net in the x direction is
15
equal to
minus 8, 7.
yeah, is equal to F applied plus Fk. But we can recognize that based on our diagram, F net in the x direction is maybe a little bit of overkill in the description because the y components are going to cancel each other out. So we could have just said F net is equal to F applied plus Fk. And so when I sub in my values, I'm just going to block off a little bit of space here because my layout is getting a little messy. F net is equal to F applied positive 15.0 newtons and Ff was equal to negative, so plus negative 8.00 newtons. And 15.0 minus 8.00, would everybody agree that it's going to be 7.0? Now, if I'm being really good about this, you'll notice that I have two significant figures in this value, but it's because when I do my subtraction rules, there's only one decimal place here, and there's two decimal places here, and when you do addition and subtraction with significant figures, the lowest number of decimal places is what determines how many decimal places will be in the final answer. So just so that you're aware of that, okay? The rules for multiplication and the rules for addition and subtraction are a little bit different. Some people forget that. Alright, so we got 7.0 newtons, and it happens to be positive 7.0 newtons, so we could say that F net is 7.0 newtons, so we could say to the right. That's not bad. And after this, we just make more and more variations on this theme. Okay, so I'm going to pause the video there.